Right. Hello, everyone. Thanks for coming. I am Dario, and I'm going to talk about the wonderful and fun world of speculative execution hardware bugs and how they affect and interact with virtualization. So a little bit about myself. I did some Linux scheduling work during the PhD in Pisa. Then I entered the field of virtualization at Citrix. Then now I am at SUSE, still doing virtualization stuff, both both of the major open source virtualization solutions such as KVM, and also I'm also doing other things at other levels of the stack, like in QEMU and libvirt. Just a very quick word about SUSE as well, with one of the first company selling Linux enterprise services. We call ourselves the open source company. We like changing how the name of the company is spelled, especially the capitalization. We make great music parodies, watch them, they're cool, and we're writing. And that's the what's this talk is going to be all about. Yes, this is the situation so far, more or less. There are other minor variants, but there's not going to be enough time to talk about these either. So let's at least skip the rest. Basically, I am going to try to cover Spectre v2. Meltdown and L1TF. L1TF is the one which is more important from a virtualization standpoint, and I would want to make sure to have time to talk about it, but I want to also touch the others because they're cool as well. Feel free to stop me and ask either during the presentation or it's probably better at the end if you have questions. And these stuff are hard. They always make me, at least for me, they always give me some headache whenever I try to figure out how they exactly work all the times. So I don't claim to, I did my best, but I don't claim to have avoided any possible mistake. So if you spot something which is not right in the slides or in what I say, do point out. So speculative execution. Speculative execution essentially means doing stuff based on guesses. So to guess something and do something else on top of that guess. In real life, it's basically like when you ask your friend, hey, do you want to have a cup of coffee? And while talking and while waiting for him to answer, you already reach out to the cup and turn on the coffee machine and stuff like that. In CPUs, the thing is that it reduces really to the fact that CPUs are very fast these days, and memory is really slow. And so while the CPU is waiting for some data, for example, to come from the memory, someone decided that it would be cool to have it doing something else, and this something else is speculation. So to just use an analogy to try to explain a little bit better what speculative execution is, and I'm stealing this analogy from another talk of one of my friends. Let's think about alternative universes, like in sci-fi, and let's assume that I can, whenever I want, create an alternate universe, that inside that alternate universe there are some roots, and these roots are that I have superpowers, because it's my alternate universe after all. And so basically I can do whatever I want. I can't be stopped. Everything I do will succeed. Then, after some amount of time, let's say 30 seconds, the alternate universe disappears, and whatever I did, the super-powered version of me did in the alternate universe, if it was good, for some definition of good, it also is applied, is copied back in the original universe. If it was bad, it never happened in the original universe. Now, one more little thing. Let's also assume that there is something which, whatever good or bad, leaks back in the original universe, and let's say that it is the alteration of the heat of objects. So basically, if the heat of some objects changes in the alternate universe, then this can also be observed in the original universe. So let's try with an example let's say that I want to figure out whether John there is looking at Facebook instead of watching my talk, right? And so I'm right now forking the alternate universe, and I can do whatever I want. So I step behind John's and look at the screen of his laptop, and then, and I forgot it. I wanted to actually bring it. Let's say that I have something like a spoon, for example, and if he's looking at Facebook, I like hold the spoon in my hand for some time. Then the alternate universe disappears. I'm back, we're all back. I don't know anything. There is another rule which I probably was in the slide, but forgot to say. The me of the original universe doesn't remember anything of what happened in the alternate universe, but I can touch the spoon, and if it's warmer than before, then I know that something happened. And can you please stop watching at Facebook? So this is basically speculative execution in a nutshell with such analogy. And this is the basics of a simplified version of a speculative execution attack. So we will look at these in some more details when speaking about Meltdown. So I will go over these very quickly right now. Let's just say that basically we need to have a way for forking the alternate universe, for having the CPU do stuff in the alternate universe, which is basically what happens in the alternate universe. What happens in the alternate universe is what we call speculation. Is stuff that CPU does in speculation, in speculative context, or there are multiple ways to call it. And then there is the fact that then there is the superpower aspect. So basically, things that the CPU does during this speculation phase really have superpowers, because things that would cause faults or errors or exceptions in regular execution, well, these rules doesn't really apply during speculation. And then there is the concept of side channels. Is a rather well-known concept for performing attacks, stealing information, and this is also used in speculative execution attacks. So you basically, instead of directly reading something, stealing some data, which you can't, you use alternative and creative ways to figure that out. So basically, the fundamental assumptions on top of which speculative execution was built, and on top of which decided to build speculative execution in modern processing, super fast processors are relying upon, is that it's possible to make the CPU do something, but then also roll it back without leaving any trace, any side effect. And that it is not possible for someone from the outside looking at or interacting with the CPU itself to reliably tell whether some particular operations, a particular piece of code, is going to be executed in speculation or not. And it turns out that not one, but both of these quite fundamental assumptions are not true. And in fact, it works very well. The rolling back of stuff that a CPU has done works quite well for stuff like registers, flags of the CPUs, but not so much with caches, TLBs, and this kind of other components, which are also part of modern processors. And also the fact that it's not possible to reliably tell whether something is going to be speculated upon or not. Well, that's not the case, because it's possible not only to figure out whether something like that will happen, but it's also possible to trigger it to happen, either maliciously or not. Of course, it's a malicious version which we care about. And so that's why, rather than hardware bugs, I mean, as Thomas was saying during the keynote, there are hardware bugs are there like forever, since when hardware exists. But in this case, more than with hardware bugs, I think we are dealing with need for us to understand that these fundamental assumptions basically don't hold, and actually they never did. So yes, I said I would talk about these issues, but with a focus on virtualization, and this is the basics of a virtualization platform, where you have the hardware, you have the host with an hypervisor. It could be, the architecture could be exactly like this or slightly different depending on which virtualization solution you are using, but I don't care about that much right now. And then you have the virtual machines, which each one of each has an operating system with its kernel and the applications inside. And these are this is the situation as far as attacks are concerned. So basically, these arrows are successful attack performed in the red case by malicious guest kernel or guest application against the host of the hypervisor. The blue case is an attack successfully performed by something running inside a VM for reading or stealing data and secrets from another VM, and stuff like that. And of course, since from looking at this picture, this situation from the virtualization point of view, and I mean from the people caring and working on hypervisors, basically, let's say technology, what we care most is to be able to prevent this kind of attacks. So the one that would allow something running in a virtual machine to read data, steal secrets from the hypervisor or from other virtual machines. So yeah, just in some more words and details what I just said, just notice that if you're dealing with these kind of attacks, so the ones, for example, which the red ones, which were about VM being able to reach the hypervisor, then these most of the time, let's say, I would say all the time, implies, for example, the VM to basically it will become able to also attack and read memory and steal secrets from other VMs. So it's one which is particularly concerning because it implies the capabilities of the other two. This Spectre v1, as I said, let's basically skip it. We'll go back to it if there is time or if you have questions. Let's just say that it's an attack. It basically, yeah, let's just say that it targets conditional branch prediction, so ifs, and a particular class of, well, not a particular class of ifs, but situations where you have a check for typically like array boundaries, and then there is some accessing the array within or outside the boundaries inside. This is the attack scenario, basically. And every CPU is affected. It's not just like an AMD only, an Intel only, an ARM only. Everyone is affected by these. There is no mitigation, basically, which sounds scary, and well, it is. But, well, it's not true. There is a mitigation, and the mitigation is going and looking and finding the vulnerable code segments and fixing them by hand, or trying to put together some tools, which is proving to be a little bit, well, not so easy. And we have mitigations in place done like that. So Spectre v2 is the one, I don't know, the one that I find particularly interesting. So it also attacks branches. This kind, if not, it's not conditional branches. It's not if. It's function pointers, so jump to something or call some function. But I'm saying function pointer because it's about jumping to executing some code or calling some function which is not known at compile time. It's stored, the address of where we are going is stored in some pointer, and we are following the pointer at runtime. Again, affects everyone. Yeah, I'll talk about leaky gadget in the following slides. And it relies on the fact that we were saying before when talking about the fundamental assumptions of being able to tell, or even worse, to trigger speculative execution inside of the CPU, basically. So, quite simply, at some point we would want to jump to some address which is stored in a register, and what happens is that we just jump there during regular execution. We go from the one there to 2. Point is that as a matter of fact, when we are up there at 1, during, for example, while, for example, something else is, the CPU is waiting for something else to come from memory, and so it has room for going on and speculating and executing instruction in a speculative way, it's possible to make the CPU think that we are not going to branch and go here, but you're going to somewhere else. And so the piece of code that the CPU will execute during speculation is not the one which then it will actually go and execute regularly, which would have speed up the execution, and which is the point of having put speculative execution in place. But it's another piece of code. And if we are able to if we manage to find a particularly interesting piece of code that we want the CPU to go and execute, even speculatively, then we could basically then use side channels technique to get, I don't know, secrets or data out of it. And this is rather scary because it affects, as I said, affects every CPU architecture. It allows, there are proof of concept showing that it allows the kind of attack that we said, even virtualization, we would want to avoid at all costs. So the ones which let guests look at the memory or steal or whatever, hypervisor data, which also imply every other VM's data. Although we must say that it is reasonably hard to exploit because as I said, it's possible to trick the processor to the CPU into executing speculatively some piece of code, but that piece of code has to exist in the context that we are attacking. So, for example, in the hypervisor or in the kernel from which you are trying to steal the information, and that it's tricky to find the correct one and execute it reliably and everything. So yeah, there are mitigations for this. Reptoline is Retpoline. I always pronounce it wrong. Is one which is particularly cool. Let's say if you have time to look at it, not in too many details, I'm afraid. So basically, I will just say that it's a clever way, purely software one, by means of which we capture the speculation in a sort of a trap, and so we lose the benefit of having the branch predicted correctly and speeding up the execution, but at least we don't leak data. Again, let me skip this slide. You will have the slide that will be online, and we can talk about offline if you want at the end of the talk. There are other kind of mitigations which are hardware ones, meaning that they come with BIOS and firmware and microcode updates from the CPU vendors, which basically adds instructions, which one then has to call, one has to insert in relevant places to have to neuter the attack. There are various ones. They have various usage and implications, which we talk about it in a minute. So basically, this means that to mitigate Spectre v2, you could use red poline, or you could use the new instructions provided by the firmware update of your CPU vendor, or someone says that you have to use the two to be, at least to be absolutely and completely sure. And for example, Xen and KVM choose a slightly different approach. They both heavily use Reptoline whenever possible and whenever safe, but they also both make use of at least some of the other firmware-based new instructions and mitigations, because it's necessary. Right, the performance impact, because this is also something important to talk about. So basically, speculation, as we said at the beginning, was meant to speed up the execution, and it did. It works really, really well for that purpose. Of course, as soon as we are starting to cripple and inhibit speculation, we are also slowing the CPU down. And turns out, especially for some case, we are slowing down quite a bit. And so, for example, the firmware-based mitigation, so using the new instructions, has quite a bit of a performance impact, which is on one end because we inhibit speculation, and on the other end, it's because the way they are implemented right now, because to add new instructions, it's very easy because the CPU vendor has the layout of the processor. It's just, they just have to change the masks, the transistor schemes, and build a new processor, which is fine. It's a little bit difficult to do it on this laptop, in which the processor is already inside. And so it's fine to do for new processors, but for the processors which are already out in the market, they had to do it with firmware updates, with microcode updates, and they turn out to be basically writes to MSRs, model-specific register, which is slow. And if you start doing this kind of operation a lot, you slow down things. There is one ARM CPU for which flashing the branch predictor, which is what it's needed to deal with this mitigation, with this attack, you need to do it by disabling and re-enabling the MMU entirely. So, I mean, it's totally crazy from a performance point of view. So, Meltdown. Meltdown is nice and easy to explain and to understand. Doesn't affect virtualization that much, to be honest, but it's useful to then talk about L1TF. So Meltdown, so let's start with the fact that we have our application running. Each application can run typically in what's called user mode, so without the privilege of doing whatever it wants on the CPU, because the component of an operating system which can do whatever it wants on the CPU, it's not every random application, it's a kernel. And the kernel runs in kernel mode. And application and kernel can access different areas of memory, because if the application could access kernel memory, that would be wrong and dangerous. However, let's say that the way in which you make sure that an application cannot access kernel memory is through features in the CPUs implemented by the operating system by means of memory management unit and page tables. And so by using the bits in the page table entries and whatever, we can make sure that it's not possible for an application to access kernel memory. At which point, since we have this way of separating the memory between app and kernel with page tables, we can very well let the kernel memory be in the address space of the application because it's faster. Can the application access kernel memory then? No, because we have page tables. Right, but can the application access kernel memory in speculation? No, yes, it can. And that's it. Basically, it's possible to trigger speculative execution, and at which point application will be able to access every piece of memory which it has in its own address space, which is mapped, we usually say. So this is basically, again, in too many details that at least I have time to explain. Meltdown attack, there is application accesses some kernel memory address which it regularly couldn't never access because the attempt to access it will cause a page fault and the application will be terminated. But if we manage to make it so that the access only happens in speculation and that the regular execution access never happens instead, then we can afterwards use side channel cache techniques to figure out which was the content of the kernel memory address which we looked at. So this is an host issue, basically, is an host vulnerability, basically, in the sense that, and that's because if you are inside a virtual machine and you are an application running inside a virtual machine, yes, you can use Meltdown to access the memory of other applications running inside the virtual machine, but you cannot read, you cannot access hypervisor memory and so the memory of other VMs because they, because they are not in the same address space. There is an exception, which is Xen PV guests, where it's the other way around. If you are an application running in a Xen paravirtualized guest, then you cannot attack other application inside the same virtual machine, but you can attack the hypervisor, which is much worse. And then if you attack the hypervisor, at the end of the day, you can also read the memory of the other application. So basically, from a virtualization standpoint, Meltdown needed to be mitigated by patching the kernel inside the guests to protect applications between each other inside each guest, and patching Xen at the host, at the hypervisor level, to protect everything, basically. It's rather easy to exploit, but we have a mitigation. The mitigation, does it have a performance impact? Well, yeah, it does. Again. No luck. Tough luck. So basically, as I said, there is a reason why we want, we did this crazy thing of having all the memory mapped inside all applications. It's because it's fast, it's because it's very convenient. But we can't do that any longer. That's this simple. That is the mitigation, basically. Let's just get rid of having memory which an application cannot access in its own virtual memory, in its own address space. And that means that expensive operations like switching the address space, so going from something which only contains application memory to something which contains both application memory and kernel memory, which is important because the application has to, at some point, for example, for doing a syscall, execute kernel memory, execute stuff which is inside the kernel. And so we switch the address space when we want, every time this has to happen, which comes at a rather high price. Turns out that there is a super cool feature in CPUs, in Intel CPUs, for example, which I wonder whether, since Thomas was saying that they knew, I wonder whether they added PCID in the case that anyone would figure out something like that. No, that's probably not the case. So basically, there is this very cool feature which basically speeds up the change of address space of an application, let's say. And no one was using it, because it's very complex to use, And we don't need it, because it's much more easy and convenient to map the kernel inside the application address space. So who cares about unusable feature which gives us speed up which we don't need? Well, now we need, because now we have to switch address space, and so we started to take advantage of this feature, both in Xen and Linux and KVM, and it mitigated a little bit the performance impact of page table isolation, which is the mitigation for Meltdown. So yes, there was an expected performance impact of 30% when this came out. It turned out that it was a little bit less than that, or well, in the sense that it's a little bit better than that because the drop is less than 30. And with PCID for typical workloads, well, it's not. It's whether it's notable or not depends on the workload, but it's not entirely terrible. So these are all other variants, which, as I said, I would skip. And then there is the other one, which I'll try to be quick talking about. Particularly interesting for virtualization, which is called Foreshadow in the, it's the fancy name, but we always call it L1TF, which basically works like this. I will explain you quickly with the pictures. So this is the application inside the virtual machine, which, as I said, there are page tables in the kernel, there are page tables in the guest kernel, there are page tables in the host or hypervisor kernel. An application wanting to access a virtual address uses page tables inside the guest operating system. There is this feature called APT, extended page table, nested page table. It has many names, but it's the same thing. It's the way which virtualization-enabled processors use to make virtualization possible, or at least fast. So basically, you have two levels of page table, one in the guest, one in the host, and the address is translated by the one in the guest, the one in the host, and then goes to the cache and memory, and then back to the application trying to access it. Of course, if for some reason, when we get here, we figure out that this is not, there is an attempt to access something which is not valid because it's not part of the virtual memory of the application, or the virtual machine, sorry, then there is a fault and we deal with that. The same is true if something happens here. There is a fault and the guest itself inside it deal with it. Now, this that I said, the guest deal with it, is for regular execution. What does happen in speculation? It happens that while we wait for the guest to deal with it, why don't we make the invalid virtual address generated by either the application or the guest kernel, forward it to the host, the hardware cache, and then whatever we find in there, send it back to the virtual machine itself. Which means that we give the power to the virtual machine to read the host RAM, or throw to the cache, at wherever it likes, basically. And that is very, 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 very bad. Because basically a potentially malicious application or kernel, it's very hard to exploit from inside an application inside the guest. You have to have a malicious virtual machine. You have to be the entity which is trying to steal data to be this one, the guest kernel, to have compromised the guest kernel. But for example, from the people looking, for example, after hypervisors, it's the other way around. We always assume the virtual machine, even the kernel of the virtual machine, to be malicious, and we have to deal with that, and we have to protect the other VMs from malicious virtual machines. So this is really, really bad, and it gets worse with hyperthreading. Because, and I will be super quick, hyperthreading means that it's possible to have two virtual machines running next to each other on two siblings hyperthread, and basically using LITF, stealing data, this one could steal the data from this other one, without for example, hypervisor being able to do anything about it because it's not even involved. If you don't have hyperthreading and you need VM1, it runs, it loads data in the cache, then VM1 stops running, there is a context switch or a VM switch in this case, another VMs arrive and can read data, the previous VM's data in the cache after the context switch. But context switch means that kernel or hypervisor happens in between. And so there is something which we could do. With hyperthreading, there is no need of context switch. This one is just running independently and without and can interact with each other in bad ways without any problem. And that applies to hypervisor data too. So basically, if something, if on one thread we are running the hypervisor code, and we have a VM, a malicious VM on the sibling hyperthread, then it can read hypervisor code without the possibility of being stopped. So yeah, there's nothing that we can actually do. The impact is huge. Basically, every virtualization solution which uses hardware virtualization, that is the two level of page table provided by the hardware, is affected. Xen paravirtualized guests, which were the only one affected by Meltdown, funnily enough, are not affected by these. It's not true that they're not affected, but there is a mitigation in that case, which is very, it's the same mitigation which you apply to bare metal Linux for protecting applications, which is trivial and has zero performance cost. And it's not straightforward to exploit because you have to be kernel in a guest, the data must be in the L1 cache, but it's not that hard either. So it's very, very scary. And the mitigation is, at this point, the mitigation is disabling hyperthread if you want to be fully sure and secure. If you know that you are a cloud provider, even if you are a cloud provider, you are in control of your infrastructure, you know the level of trust of guests, then you can say that you leave it enabled because of things that you do, and if your customers buy it, then fine. And most of the time, it's probably even true. I'm not claiming it's not. But it's not a full mitigation. It's a mitigation if there are some other things in place, which everyone can try to do in its own way. But the full mitigation at this point is just don't use hyperthreading. And the performance impact is the one which we get by disabling hyperthreading, which varies. It's not like the number of your CPUs will be cut to half if you look at it, but as a matter of fact, it's not really halving your performances because hyperthreading never really provided 2x speed up. Still, it might be noticeable, especially under some workloads. And alternatives idea, and really I'm finished, sorry. Alternatives ideas for mitigations, they're in the work or they're being thought about. These lists, for example, there is this very good talk about my colleague Alex Graff at KVM Forum. He also has a demo about L1TF, it's very cool, which is drafting basically this idea. So you can use other things. Basically, for example, other ideas as to not use the nested page table, which so basically get rid of also the these capabilities of provided by hardware support for virtualization, which is what was being done before hardware virtualization was a thing and was lower. So yes, you can do that, but you are going to lose performance again anyway. And it's even slower now with Meltdown mitigation in place. So that's not exactly something we are sure we could deal with. We can work with the scheduler, and on top of that, do also other things, but that's very complex. And well, stay tuned, because we don't know yet. Yeah, that's it. The mitigations on each virtualization platform, there are tunables for the various mitigation. You can enable, disable, choose the variant that you want. And if you care about this stuff, you should actually figure this out and check the impact on your workload of the various mitigation and choose the best one, which is, after all, the conclusion of this talk. Basically, these stuff are difficult to deal with because of the secrecy involved, as we learned during the 2 keynotes. Difficult to deal with because they are difficult technical problem. They are real. They could lead to stealing of data and to real risks. The performance impact is also real, but instead of just running away screaming, the wise thing to do is to assess the risk, assess the performance impact, and try to choose the best solution. After all, we went, or at least the other vendors went for a performance-first approach, and now, my grandma says, evoluto la bicicletta, ora pedali. Which means we have to deal with the consequences. Right.
Thank you.